8.2a, so it's the second question on your second practice exam. So this is very similar to the question on your last test that looked pretty much the same, except that this is a second order ODE, so we have to differentiate one more time. It makes it slightly more complicated, but very, very doable overall. So we're going upon the same base assumption that our solution is going to look like this. Cn, S and x of n minus a. And luckily for us, in this case, a equals 0 because our power series is centered at 0. So taking our first derivative, infinity, and do note that your index is changing because when you evaluate this at 0 and take the derivative, it is 0, so it's kind of a useless term. So that's why your index is changing. So you have n Cn x to the n minus 1. Okay, and then y double prime equals the summation, and then n equals 2 on this one for the exact same reason it did here. So if you want a good way to remember what your index is going to be, you can choose whatever is going to make your exponent equal to 0. So the whole thing here is when you evaluate this, when you start the count at 2, this x to the 0 goes to 1, and then you're left with just a constant here, and the derivative of constant is 0. So that's why it's kind of like a useless term, as I say. So hopefully that explains that a little bit more. So now we are going to plug that back into our original differential equation. So we get the summation n equals 2 n minus 1 Cn x n minus 2, and then plus x summation sigma n equals 0 Cn xn equals 0. So that's our original equation, and now we are just going to manipulate it a little bit to make it look a little prettier and look a little bit more like we can use it. So the first thing I'm going to do is I'm going to distribute this x term. So that makes our equation go to sigma n equals 2. I'm sorry if this is messy. I really am trying my best, guys. I promise. So n minus 1 Cn x to the n minus 2. And then when you distribute this x term, it's going to show up as an extra plus 1 exponent on your original x term inside the summation. So you get Cn x to the n plus 1, and this is still equal to 0 because we're still comparing it to our original equation. So I'm going to try to make my screen smaller. I'm sorry if this makes a horrible noise on the video. We'll just see how it goes. I'm still trying to figure out how the best way to do this is. So please be patient with me. So I'm just going to take this and resize it so we have more room to work on the rest of the equation. Hopefully that's still readable. Okay, you know, I'm actually gonna make it a little smaller so we have even more room because I feel like it's still readable. Okay. So back to our problem. So we got it into this format, which is a lot closer to what it needs to look like, but not quite what it needs to look like. So similarly, as we did on the last test, we are going to re-index. So we need the exponents on the x terms to be the same. So for this to happen, okay. for this term, I'm going to set whatever my exponent on my x term is to equal to k or m or whatever you want to set it equal to, honestly. N minus 2. And then so for this one, k, man, that's a really big k. K equals n plus 1. So solving these around, you get these two statements. And you pretty much just plug them in everywhere into your equation. So once you do that, you're going to get a new summation formula, and it's going to look like this. That's k. That's a k, guys. K equals 0. That's a 0. Sorry. Slowly getting worse as we go. I kind of lost track of where I was. Oh, I'm sorry. That's not what I want it to look like. I really just want that end on. Okay. So okay. K still equals 0. But plugging in those values, you get k plus 2 times k plus 1. I'm sorry my k's are so ugly. But you know what? We're all in this together. K plus 2, and then times our x of k. Okay, so that's the reindexing for that one. And then for this one, we're going to reindex it the exact same way, just applying those equations. So now we get a k equals 1 here. So c sub k minus 1 x of k. Okay, so that is a step closer to where we wanted to be with our exponents on our x terms being the same thing. So we're a little bit closer, but before we can combine the summations, we have to get the index in the same index as well. So to do that, we're pretty much going to take this 0 term here. So we're going to take k equals 0, and we're going to evaluate the first summation at that. So evaluating the first summation at k equals 0 gives you 2, that's a 2, times 1. So the 2 times 1 comes from the plugging in 0. So 0, plugging in 0 for this k, and for this k, you get the 2 times 1. And then plugging in a 0 here for this k gives you c sub 2. Okay, and we all know that when you plug in a 0 for the x to the k, you get 1. So we just know that this is a term that exists in our equation now. So now we can combine our summations, which is nice. So now they're both starting at k equals 1. Oop, that's an infinity. So we get k plus 2, k plus 1. Okay, and then c, I hope I have room to write this. K plus 2, I might not. Okay, next k plus ck, I'm going to try to like really squeeze it in. Ck minus 1, and then x to the k. So you can factor out the x to the k, and I'm kind of wishing I would have done that already because now I just wasted a line, but whatever. We'll just rewrite it. C2 plus, okay, plus summation of k equals 1, well, starting at k equals 1, of infinity, k plus 2, k plus 1, ck plus 2. I'm so sorry, this is so messy. I'm really putting in effort. And then plus ck minus 1 times x to the k, and this is all equal to 0 still. So based on this equation, we know that this and this have to equal 0 simultaneously for this to be true. So we know that C2 equals 0. Okay. And it's C2, I forgot to mention, it's C2 for the same reason when you plug in the 0 here. I know that can be a little confusing as to what C you're solving for, but just keep in mind to plug in the 0 for your subscript as well. So now we know that C2 equals 0, but we also know that this little fun equation equals 0 too. So you can solve that however you want. I'm going to solve it for the CK plus 2 term because we already know that C2 equals 0. So if we start at 1, we'll immediately get C3. And we don't have to work with negative numbers or anything like that. So similarly to the last problem on your last test, once we got a constant value that we knew, the values before that became constant because we can't solve for them. Well, I'm sure we can solve for them, but we're not going to on this problem. So don't worry about that. Okay, so now we're going to get just a general equation like we did last time that we're going to solve for all the coefficients for. So algebraically, you can do this. Hopefully it makes sense. If not, maybe I'll upload how to do it later. I'm really trying to put an equal sign there, and I'm really just putting a bunch of random dots, but that is an equal sign. And then here, let's do k plus 1. Okay, so that is the equation that you're going to be using to find all of these coefficients. So luckily, you've actually already solved for the first 3, and you're only asked to find up to x to the 6th. So this one doesn't take quite as much time. And keep in mind, once you solve for these coefficients, you're going to have to plug it back in to your format here. X to the n, that's also an n. Okay. So with this formula, you can solve for all the coefficients, and I'm going to make my screen smaller again so we can get on to that part. Yet again, run out of room. I'm sorry this is gonna, like each part's gonna drastically get smaller every time I run out of room, but hopefully it's not too confusing. Okay, make this little buddy smaller. I don't make him too small, but I also want to be able to finish the problem, so let's do it over here. Okay, that looks a little bit weird, but hopefully it's still legible, and hopefully you've been taking notes, so you won't have to go solely off of that. Okay, so now that we have our base equation here, now that we have our base equation here, we can start plugging in the values that we know. So because we chose the C sub k plus 2, we can start our count at k equals 1 because it will yield C3. So when you plug in all those values, here you get a negative and then ck minus 1, so our k equals 1, so c sub 0, and then k plus 1, k plus 2, if our k equals 1, that gives us a 3 and 2, so we get a negative c naught over 6. That's a naught, I don't want it to look like a 1. Okay, so that is your first term, and that's negative. Okay, so for k equals 2, you'll get C4. And for C4, C sub 4, so k equals 2, meaning you'll get a negative C1, and then over a 4 and a 3. So this time you're going to get a negative C1 over 12. Okay, and then for k equals 4, you'll get, oh, I guess we should do 3 first. Maybe, if I can, like, get this to disappear. Oh, I'm dumb, and I'm not going to worry about it. We're going to do C4 first, and I'll go back and do C3. I mean, k equals 4. Sorry, I'm a little scatterbrained. So for k equals 4 is going to give you C6. And here you're going to get our C naught again. C naught again, and then over -30 and -6. So that's actually going to go to a positive C naught over 180. So now I'm going to go back and do k equals 3 since I forgot to do it the first time. So k equals 3 gives you C5. Oops, C5. When you plug in C5, you're going to get a C2 over 4 and then times 5. So here, it doesn't really matter what these bottom numbers are because we already know that C2 is equal to 0. So this whole term will go to 0. And that's it. Those are all your coefficients for the solution to your power series. So don't forget to plug it back in to this little guy over here to get the actual, the way you're supposed to write it. So just a preview, you'd write something like y equals C naught, okay, C naught. So C naught doesn't have anything because it's a 0, so you'll have an x to the 0, which goes to 1. So you have C1 and then plus x and then plus C2 x squared, and then you just continue on that pattern. But obviously plug in your coefficients that we solved for in this portion of the video. So hopefully that wasn't too scattered and it made some sense. Please let me know if you have any questions. Hopefully it's not too bad, but I'll try to do my best to help you guys through these next few exams. So